The next thing we want to talk about is regression. And regression is the line that can be fit to your data, or the line of best fit, which you may have heard about in the past. And a regression is a line such that any given y equals a plus b times any given x. So it's a linear relationship between y and x. And in this equation, a equals the intercept, so it's the y-intercept for x equals 0, and b is the slope, and b is a unit increase in y for some unit increase in x. The goal of running a regression is to predict y from x. There are a few assumptions to the regression. One, that there is a random sample. Two, that y is normally distributed with variance independent of x. And linear regression assumes that the relationship between x and y can be described as a line. And so if the relationship is curved or has some other shape, then a linear regression does not work. I want you to note that x does not need to be normally distributed in a regression, only y. This is different than in correlations. So running a regression in R is pretty simple, and we use the linear model, or LM, function. And we give the model some name, here model.1, it doesn't really matter what the name is, and it's LM, and then it's your y variable first, so here is y2, and then you have the tilde symbol, and then your x variable. So here it's the linear model of y given x. And if we run that, it will give us our model parameters. And if we want to look at the results of our linear model, we want to run the summary of model.1. And if we take a look, and I pasted it here in the script, we have call LM formula equals y2 given x1. Okay, that's correct. We are given some information of our error, or our residuals. The residuals is the distance between a given point and the line of best fit. We don't need to worry about those for right now, but we are interested in our coefficients. These are the components of that line equation that I introduced earlier. We have our estimates, our standard error, our t-value. We're actually using the t distribution to calculate a t-statistic. And we have our p-value, which is based on, of course, the absolute value of our t critical value. We have two rows here. The first row is the intercept. This is y when x equals 0. The intercept is 16. The t-value is 29.925, and we have this extremely small p-value. The intercept is typically not that interesting except for this estimate here. Basically what this p-value is telling us is that our intercept is significantly different from 0. So for our line of best fit, it doesn't cross 0 on the y-axis when x equals 0, which is interesting but not really important for our predictive power. However, you might find this interesting if you are comparing two different lines and you're interested in whether the intercepts are in the same location. What's really interesting here is our x1, because what this is giving us is our slope. Is our slope significantly different from 0? And so our slope, or our b, is 0.3187. Our t value that was calculated for us was 1.115, and our p-value is 0.289. which is greater than 0.05, and therefore not significant. So our regression is not significant. This shouldn't be that surprising because our correlation was also not significant. There is a r² that is given to us. This is the proportion of the variation explained by differences in our data. Here it's 0.1016, so that means that around 10% of the variation is explained by differences in our data, but the regression is not significant, so this information is not really useful. It's only useful if our p-value is less than 0.05. So here I've written out the different parts that are important for you to review. So our slope, or b, is 0.3187. The intercept, or a, is that estimate 16. And we can write out the full linear equation as yi, there's some given y, equals 16 plus 0.3187 times some given x. One thing to note about b is that a positive b means that there is a positive relationship. As x goes up, y goes up. If b is negative, that indicates a negative relationship, and so as x goes up, y goes down. We can plot this line really easily in R. I'm going to run paramifro 1, just because we're looking at one plot here. And so let's plot our example data. You can see it looks pretty flat. It's really not much change with y given a change with x. But we can use this function called AB line. And so AB line, you have A, which is your intercept, and you have B, which is your slope. So AB line, and then we add in our model. So our linear model is, we named it model.1. We, let's say, give it a color, let's make it red, and then let's make it a little bit thicker. So LWD is the thickness of the line. I said 3, you can set it whatever you want. And if we run that, you can see, okay, our line is pretty flat. So here you notice that x goes from -4 to 4. We can check to make sure our intercept makes sense by looking at x equals 0, and it's right here. And if we kind of eyeball, look up here, and then we come over here to the left, yeah, that's pretty close to 16. So, and actually we know it's exactly 16. So this looks correct. And here the line is not significantly different from 0, therefore x is not predictive of y. Y does not change in a predictable way with x.